Hello, Houston. We had finished a delightful interview last time, and we're launching into decision-making. Before we start that, I did want to correct one factor in my introduction. When I introduced Professor Ann Jacobson last time, I neglected to say one other important feature that I wanted to mention about her illustrious career, and that is the fact that her PhD actually comes from Oxford. We are quite blessed that she's spent the majority of her career here at the University of Houston, but you can kind of sense that from the far-reaching array of topics that she folded into what she was talking about in that interview, and I hope you enjoyed it as much as I did. It was a delight to have her here with us for a brief little while. So today what we're going to do is look at a couple of different ways in which we can analyze and make decisions, essentially. So we're going to be looking, first of all, at what I had started to introduce last time, and that was the rational normative models that are involved in decision-making. And without taking time to spend a whole lot of time on it, I'm just going to go back and refresh you on the fact that we talked about two different types of decision processing that can be done. One leads to rational decisions, the other is an irrational decision. And the only basic difference there is in the one word that I highlighted for you on the last lecture, and that is, if you notice, the two definitions are precisely identical, and the only difference is that in one case, using the when the conclusion ultimately is irrational, what you've produced is contradictory conclusions, and in the other case, when the decision making is rational, you've followed confirmatory conclusions in terms of whatever it is that you're debating and trying to make decisions about. There were a couple of other ways to define the rational decision making, since that obviously is what we tend to spend most of our time on, trying to understand human logic and so forth. And in fact, we could even push that to a single word, and that is the fact that when the decision-making is rational, it is typically logical in the processes that we're engaged in. So with those goals, as those goals change, the model that can be applied in a particular situation may also change. So that the pertinent question that we're dealing with then is really, what are the goals of the decision maker? And those, of course, vary. You know it in your own life, to get up or not to get up, to invest this money or not, and so forth and so on. So there are at least a couple of different models that really put, as you'll see when we get into it, a slightly different emphasis on the material we're using to make whatever decision we're about in the midst of trying to bring to fruition. One of the more interesting and classic approaches is what's called an expectancy value model, or a theory of decision making, and this can be applied in several different ways. But there are basically two variables about which we have to be concerned in this particular model. One is expectancy, and what we're talking about there is the expectancy of the occurrence of success, that is, the expectancy of succeeding. And the other is the values that we hold which are impacted by these particular expectancies. That is, what are we trying to achieve and what is the likelihood we can do so? If you're a basketball player, you would not likely want of marginal value. It would probably not be beneficial either to you or to him to spend a whole lot of time on the basketball court playing against Yao Ming, because he could simply stuff the ball back in your face anytime you shot from almost any angle. And in that case, your expectancy of success would be quite low. If we found you doing it anyway, the likelihood would be that you had a lot of a value attached to simply interacting with such a luminary star. But the expectancy of success in that kind of one-on-one would not be high. I expect you'd be willing to grant. So let's convert that into some very specific examples, okay? Let's suppose, for instance, that in talking about expectancy and value, the expectancy of success in a particular wager that you're likely to make is that you can win $20 on that wager with, say, a 0.2 likelihood that success will come your way. That is, the expectancy of success in this model is simply 0.2. And so if we multiply it, in the long run, what's going to happen to you is that with the investment that you make, the net return on a 20% likelihood of the event occurring will be $4. If you look at all the possible times that you try to win the 20, the net outcome will be $4. Okay, the probability times the ultimate win. But let's, on the other hand, say, well, okay, let's change this a little bit. Let's say that you can win only $15, but we're going to do that with a 0.25 possibility, 1 in 4 chance of actually winning. Well, when you multiply it out, the net result is that this situation, lower reward but greater probability by 20%, actually yields less return. And so most people in that kind of a situation would rationally tend to vote with the greater return on a slightly less likelihood, given that the ultimate return over the long run would be slightly higher. And so the result is pretty easy. Your long-run gain would be $4 in the first instance. It would be only $3.75 if you took the second option. So most people, faced with that simple kind of a presentation, would opt with number one. Casinos and betting establishments, if you think about those as an institution where the odds are at play all the time, really are a remarkable human invention if you think about it. And they are sub rosa sensitive to the issue that I'm going to raise here, and that is if you think about driving to New Orleans across the Chefalea Swamp and everything else, the ads between here and the nearest casino in Louisiana always stress 99% return on your dollar. And they stress the return to us of putting money down on the table. 99% of the time we're going to get our money back. But the other way to look at that is simply 1% of the time when you put that money down, it's gone. And so the net result is that really, I think it is ultimately fallacious for any of us to walk into a casino with the idea that we're going to make a big kill here. It's going to happen. Because the odds that I'm talking about here, and I'll show you a couple of other examples, do shift in terms of how you and I decide based on what's most important to us. But the ultimate financial rationale for gambling at all is simply not there. Because, of course, ultimately you have to realize that those casinos are not in business to give us money. That's the tease. That's the thing they pull us in with. But they would go out of business if all they did was give people like you and me big wins all the time. And the thing that always strikes me as amazing, and the little impact that it has on gamblers, is the fact that if you think about pictures that are occasionally seen in gambling establishments, and they don't allow many of those, but if you look at the hundreds of machines that are lined up there, you don't tend to see red lights and bells going off, bells. You don't tend to see red lights flashing and an obvious winner in that case. What you've got is hundreds of people spread at the one-armed bandits pulling the arms, simply having put money in. And the gamble is, will something happen? But if you look across all those machines, it doesn't tend to happen very often. And that's one of the reasons that they have so many bells and whistles and lights and everything else that happen when you do have a big winner, because they really want to attract attention to those people as rarely as they happen. So they're really feeding into, despite the odds that we're going to review here today and the rational decision-making that goes on, if you're hooked on gambling, other things are going to happen. There are just other things that are more important to you. And in one sense, when I've gone into gambling establishments, I simply set a dollar limit that I'm willing to invest that day. And I figure it's entertainment. You spend a certain amount of money to go to the movies, whatever. And so you figure that that's the money you're ultimately going to lose. And 99 times out of, in fact, every time I've gone into a gambling establishment, I have lost, ultimately. So you just pay that much money for entertainment. But let's look at this in a slightly different way. And that is expectancy value theory actually also bears on a lot of other things than the way we invest money. And I'll get back to that in a minute. But you think about it, in a dating relationship, there comes a relatively crucial point early on in the dating relationship, and that is to kiss or not to kiss. One or the other partner, fairly early in the relationship, if it's going to develop into something, faces the situation of, when do I make the move? And so if you've been out on a Saturday night date and it's been rolling along pretty well, he or she has been laughing at your lines and you've been laughing at theirs, and it's been a good, enjoyable time. So you're sitting there thinking to yourself, do I make the move now? And at that particular point, you're thinking to yourself, it's been a good date so far. 0.8 likelihood if I make a move for it, it'll work. Okay? So in this case, if the expectancy is 0.8 and we've just arbitrarily assigned 100 points of positive value to kissing that other individual, you've got 80 points on the ledger in your mind saying go for it. But there is one key element that also contributes to that, and that is the fact that if you initiate that kiss, what may happen is that he or she kind of checks the watch, says, oh darn, I've got a meeting, I'll see you, and they're gone. That's not what you were after, but in essence what that leads to is significant personal embarrassment. Most of us do not set about to embarrass ourselves, and so there is a high negative value that is associated to that. Negative 500, mythically chosen in our particular example here. But with that only 0.2 likelihood, you're pretty sure that, if you make a move, it'll work and you'll be fine and off to higher stakes. But in essence, because of the negative value that you attach to that embarrassment, none of us likes to be embarrassed. Very few of us rush from one situation to another, just striving for greater and greater embarrassment. So you have a high negative value attached to that, even though in this particular situation, given how well the date has been going in the meal, the odds are very small that that'll happen. But when you multiply that expectancy times that negative value, we don't like to be embarrassed. The net result is that there are 100 points to the negative in our model here saying, no, don't go for it. Don't make a move at this point. So the net result is, if you add it all up, you've got 80 saying go for it and a negative 100 saying don't go for it. The net result is you've got 20 points to the negative saying, no, I'm not going to make the move at this point. And then all of a sudden he or she leans over, puts his or her head on your shoulder and goes, instantly, 0.8 becomes 0.99, 0.2 drops to 0.01, and when you do the multiplication, now what happens is you've got 99 points saying yes, and only 1 point arguing no, or sorry, 5 points arguing no, let's be cautious here. And so the net result is a positive 94, indicating yes, you'll make the move at this point. That is essentially the operation of an expectancy value theory. What's interesting about that theory and the group that I'm talking about here today essentially is that the expectancies are momentarily adjustable. That is, those are where you and I are predominantly making our decisions, is what happens moment to moment, based on the fact that most of the values that we possess, how much we like person X or person Y that we're dating at that particular point, and the instant assessment of what's going on socially between the two, it's the value that is stable. You know, I mean, the idea of setting up the date on a Monday that's going to happen on a Friday or a Saturday is consistent with the idea that that value is fairly consistently held through that. It may ebb or flow a little bit, but it's fairly stable. And on the other hand, the instant expectancy of your assessment of likelihood of success is momentarily adjustable based on what's happened. And if you insult the person at some point, the expectancy may drop for a while until you explain what you were trying to do and why you were trying to do it. And then the expectancy comes back up as they come to understand what you're talking about. And those expectancy values go all the way around to applying for a loan or something like that. I mean, you may go in with some wrinkles on your credit record, and when you ultimately sit down with the manager of whoever makes the decisions and explain what the situation is, why event X or Y or Z happened, and they come to understand what the context was within which you offer or operate, the expectancy of that person deciding positively may go up. The value of you as a customer is, of course, largely unaffected there. They're interested in loaning money to people and in turn making money on you and I. So in any case, the expectancy value theory applies pretty widely. Let me show you another example of a different type of theory that has very much the same kind of logic behind it. And those are a cluster of demonstrations that are called essentially expectancy utility theory in that situation. And in this kind of a theory, expectancy is essentially defined as we were talking about before. That is the estimated odds, your estimation of success. And you may not actually think it through in that much logic, but that's in essence what's operating behind the theory when theorists make predictions about what will happen in a given situation. But utility in this situation in this model actually refers to personal value, not to monetary value. So the expectancy value theory was in some, or the model I gave you of to kiss or not to kiss, I couldn't decide whether to put it under expectancy value or expected utility. In some ways, you could easily rationalize that it was more an example of expected utility, expectancy utility of the model here. So that the basic difference is that the value in the previous theoretical analysis has to do typically with money. That is what you're dealing with when you go over to one of the casinos in Louisiana. And expectancy utility theory, or expected utility theory, really is dealing much more with the actual value to you as an individual in a given situation. So that axioms have been developed around these types of theories basically to describe a whole variety of decision-making situations that you and I face more or less constantly. Now, assuming that your decisions follow the axioms that have been built on the theory, derived from the theory, your decision can be predicted once we can specify the utility value of that subject to you and your estimate of the expectancy of success in a given situation. Let's take that previous example that we were talking about and put it in a slightly different situation, a utility model that looks at essentially the odds like the following. That is that the expectancy of success to you personally is in this case $8 if we've doubled the odds of success from the previous model. Okay, the previous one was talking about $20 with a 20% likelihood. Here we've doubled it to 40, and therefore the results in both cases we've doubled 0.25 to 0.5. And in fact, when you do the multiplication now, the ratio of winnings to possible winnings in each situation is stable or similar. But the absolute value that's involved is quite different. Well, in fact, let's double it one more time, okay? And then let's put it in a very specific context, and that is suppose that you actually need $15 to take your significant other to a movie. You decide at some point that you want to go see movie X with him or her, and you're going to fund the effort since it was your idea, and you need $15 to get the two of you in the door. Now you've got a particular wrinkle on reasons to want to invest some amount of money in trying to come away with $15 or $16. And herein lies the kind of interesting wrinkle that lies in this overall process of decision making. Because in this particular instance, the 80% is the preferred mode to go if you're going to do this over the long run. That is, in the multiplication that I've done there on screen, you can see that although the odds of winning are 0.8 rather than 1.0, the number of the dollars that are involved are enough higher so that you can tolerate the 20% risk. Because in the long run, if you invest the same amount of money over and over, the net result will be $16 of wins, given an 80% likelihood of winning the 20. But your need immediately is the $15. And so what happens is that you tend to swing, and in this case, you will prefer the less favorable outcome because in terms of your immediate needs, it does in fact match those needs. That is, you need the $15 to get into the movie. And so in this particular case, and for a variety of other reasons that we'll talk about, you tend to swing with the other option, partly because it's certainty, even though you know in the long run, if you keep doing that, you're not going to win as much as you would if you went with the 0.8 option in that situation. But in essence, it is a kind of a funny thing that happens here, and that is as your own expectancies or needs change, as the expectancies change, which one you'll follow may also be impacted. And so in this particular situation, the only thing that is likely to swing you back to the lesser certain, where there is some risk of not winning, is if that other dollar has some particular significance in your in your life. But in terms of what you're intending to fund, $15 is all you need to go to that movie. And so that becomes the preferred option, even though you know in your own head, this is stupid because in the long run I'm going to win more money if I go the other route. But you can't be certain of that. And in fact, that reversal leads to or is based on what is sometimes referred to as the certainty effect. That is, certainty will often bias us, even though it's counter. I'm going to show you some examples here a little bit later, where you will, because the outcome is certain, you're more likely to follow that than you are one where there is some greater risk, even though you can see in the long run the return might be greater to you in any particular situation. So in fact, let's look at some of the violations of the logic that I've so coldly laid out here so far. And in terms of violations of expectancy utility theory, or for that matter, variations of expectancy value theory, what you find is a rather interesting thing called the Elias. I've never known how to pronounce this correctly. It's either the Allais paradox or the Elias paradox. Expecting that it's been Americanized, I'm going to go with Elias, but trust me, I may be absolutely wrong on that pronunciation. Didn't get to ask a fellow professional how to do that. So in any case, what was posed here is a rather interesting series of problems with the following kind of choices that are offered to you. And so I'm going to lay out several possible situations for you. Let's suppose that in situation A, among several I'm going to give to you, there is, in this case, the likelihood that you can win $1,000 with a perfect certainty. That is, the odds of you winning 1,000 are 1.0 in that situation. Let's pair that off with an interesting other possibility, and that is, let's pose the following situation. Instead, we're going to put you in a situation where you might earn that $1,000, and we'll keep that pretty strong, say 0.89 possibility, but 89% likelihood that you'll win that $1,000. For 10% of this, we're going to give you $5,000 as the reward. So you've got a 10% likelihood that having invested your buck or $2 or whatever, you're going to win $5,000. 0.10 likelihood, just 0.1 likelihood that you'll do that. And of course, just to keep it interesting for you, there's a 1% chance that you won't win anything. There's a 0% likelihood. Just that relatively subtle change significantly alters the likelihood of what choice we'll make. And I'll show you how we can even change that. But in this particular situation, what most people will do is to select A over B. That is, that certainty effect I was talking about a minute ago jumps right in here. And we tend to go with the certainty, even though you can see that there is a greater likelihood. I don't know whether I'm going to add up the results here in a minute, but it's several tens of $1,000s above $1,000 a pop if you do it over a long period of time. That is, there's a significant reason to switch in terms of what we're doing if we run it 100 times or something like that. But no, we don't tend to take the chance. We go with certainty because the win is there. There is a guaranteed income in that kind of a situation. Then let's put a couple of other wrinkles on it. Let's give you choice C and choice D. So now we've changed it ever so slightly. As you can see, there's an 11% likelihood that you're going to win $1,000 and an 89% likelihood that you're going to win no dollars at all. There is a slightly less likelihood in choice D that you're going to win $5,000. So we've increased the amount of money at risk by five-fold, and we've only very slightly cut the odds, seemingly making this a much more attractive option. There is now not an 89% likelihood, but a 90% likelihood that you're simply going to lose everything, that you'll have no win at all. And what happens in this case is that people tend to select D over C. Therein is one of the reasons that psychologists end up studying this kind of thing, because the odds, you know, we've essentially removed 89% of the likelihood that you're going to win $1,000 in this shift. Okay, and yes, we've added the $5,000 option, and that's actually stable in both cases. But the main thing that we've removed is the relative certainty of winning $1,000, and yet that change, that shift in the overall ratio is enough so that people will go with A and D when they're given either A or B and C or D. They're more willing to tolerate the uncertainty in the D option than they were in the A option, and therein lies a bit of the paradox that we're talking about here. People would not give up a certain $1,000 to risk winning in the chance situation of A versus B. They are willing to do it in C, and therein in C versus D, and therein lies the kind of strange element of this, the paradox, as Allais was talking about it. So that basically, in games that are involving outcomes from epidemics, we end up with a rather challenging illustration here. In fact, there was one other thing I'd added here, forgot, I want to talk about that. So let me go back and just show you the specific dollar amounts that are involved. So I'm kind of adding up or multiplying and totaling the winning in each of the four situations here. And they're really quite startlingly different. Because in option A, the odds are simply 1 in 1 that you're going to win $1,000. So if we repeat it 100 times, your net winnings are $100,000. In option B, in the long run, 89 times out of 100 that you do it, you win the $89,000, or you win $1,000, which totals, of course, to 89. There's a 10% likelihood you get the $5,000, so over 100 trials, statistically, that will kick in $50,000. And the net result then is, of course, the last one offers nothing, only 1% likelihood. But the total winnings across this degree of risk or uncertainty is almost 40% greater. And yet we still go with A in the long run. Most of us will face that and still opt with A because of that certainty factor I was talking about, the certainty effect. But then if you put it over in the other situation, the winnings or the proportionality of winnings changes quite substantially. Whoops, I jumped too far here. Back up a second so we can see that. Okay, in that situation, I missed my numbers. Okay, I didn't finish the work I was supposed to do, but in essence, we can total it up that here you've got $11,000 with a high degree of certainty you're going to lose this, and in this case, you've got $50,000. So there's almost a 5-to-1 switch in the ratio. And in this kind of an uncertainty, given the relative similarity of the odds, but the much greater reward, people will switch and take D in this situation. So we've got, $100,000 here, $139,000 here, $11,000 here, and $50,000 here. And so you might explain it just in terms of the odds or perhaps in terms of the overall winnings. But in either case, there's a paradox because the logic of A versus B and C versus D switches when you go to the second problem there. But then what I started to lead into was you face the same kind of situation even though you may change the basis on which you're conducting the demonstration of it. Let's suppose, for instance, that what's involved here is an epidemic which is sweeping some islands, and people in that kind of a situation, if they have to select which medicine, which treatment we should use in that situation, what people prefer is an 80% chance of being able of losing 100 versus a 100% chance of losing 75. If you've got an epidemic and you've got to choose between two different choices, if one of the choices gives us an 80% chance that we're going to lose 100 people, and the other choice gives us only a certain chance that we're going to lose only 75% of the people, that bias is such that we will tend to choose the 80% risk of losing 100 against the 20% risk that we can save all 100. That's the trade-off in that situation. But then if we change the odds a little bit, now we've got a slightly different situation, and that is the situation where there is, in this case, they prefer a 10% chance of losing 75 people to an 8% chance of losing all 100. Okay, and so in this case, they tend to go with the unlike the switch that we saw in the previous use of money, in this case where human lives are involved, the basis for our decision making tends to change. And so in this case, we're going with we're willing to tolerate a certain amount of uncertainty against the likelihood that we can save a certain number of people. So the certainty effect is illustrated by our overweighting of certain outcomes and underweighting of certain other outcomes in various situations, even when the uncertain outcomes lead to a statistically more favorable outcome. So since there's a chance that I can save a greater number of people, we tend to opt for that. Even though statistically in the long run, that's not the safer option. You will ultimately, faced with that decision many times over, save more people by going with the lower number of certain saves than the risk that you may be able to save a higher number. Faced with this kind of confusing and multi-influenced logic, we can also look at a rather fascinating thing where we end up going about reversing our preferences in a given situation. For instance, let me give you another set of choices here with the odds and the amount and so forth. And in this case, let's look at problem E versus problem F. And in this case, if we're looking at chips that are worth $1, if you want to put it back into money terms, the odds in this game E, are essentially that the odds are 11 out of 12 that you're going to earn $12 plus 12. They're 1 in 12 that you're going to lose $24. One of the chips will end up costing you $24. In the parallel situation, now we've changed the odds, we've also changed the amount rather significantly. Okay? It turns out the odds are now only 2 in 12 that you will earn $79 with the chips. The odds are 10 in 12 that you're going to lose 5. Which do you go for in that situation? Or let's do it another way. In fact, all of the options are there. I didn't realize that I'd put the second choice up for you here. Theoretically, what should happen there is an equal choice. Because if you do the math, and the figures are deliberately a little bit vague, so you can't work it out neatly, but the odds are essentially $108 as the net outcome over a significant number of plays. 10 plays will generate $108. Because in the left situation, you're going to win 11 out of 12 times. That means $132. You're going to lose $24 one time, so we subtract 24, and the net win is $108. In the other case, you've only got 2 likelihoods out of 12, you'll get 79, but that gives us 158, to which we add the $5 that we're going to lose 10 out of 12 times, or negative 50. So the 158 minus 50 comes back to 108. So given the difference here, the net winnings are going to be the same, and theoretically, therefore, it should not matter which of the two we tend to do. Most people, in general, faced with this kind of a choice, will be about 50-50 as to which of the two choices they make in that situation. What this is leading up to, though, is easy to get to from this, and that is that what really governs what we end up opting for in many instances is the framing, how the thing is presented to you. So for instance, just as a puzzle, and I don't want you to use a pencil on this, but just use your head a minute and figure out what is the mathematical sum, roughly, of this mathematical equation. That is, if we multiply 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, what do you get by way of a conclusion in terms of the sum, roughly speaking? And then, would you rather do that in a gambling situation or any situation where you're trying to multiply what you got, or would you rather look at a situation like this, where we start with 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8? And what would you estimate would be your winnings in that situation? And it turns out that the likelihood of being able to attract you into either one of those is a result of the order in which the numbers are presented to you. Because it's very tempting, as you may already have anticipated, the actual correct answer is 40,320, which of course you knew immediately. But in essence, when we start out with big numbers and start multiplying 8 times 7, the very first number is 56. And yet when we're multiplying the same 8 numbers in the reverse order, 1 times 2 is 2. Times 3 is 6, times 4 is 24, times 5 is 120, times 6 is 720, and then you're starting to get into big numbers. But you're through 3/4 of the numbers before you even get to 720. And that basically is referencing what is referred to as the framing effect. And that is, people's being attracted to one or the other of those two options is very much influenced by how the problem is actually presented to you. And that is called the framing effect. Essentially, as defined there, a change in decision resulting from differing forms of presentation of identical data. And the two things to pick out there are the words identical and different forms. What creates the framing effect is simply how you actually present the situation. Okay. This was originally picked up and studied. The problem was originally posed by Kahneman and Tversky, Amos Tversky and Daniel Kahneman, in an article in 1974, what has become a classic article in 1974 on the overall effect here. But in essence, I'm just jumping ahead to make sure I don't skip a problem or an illustration that I wanted to give to you, because it will definitely show you. Well, I'll hang on here and I'll come back to it if I have to. But in essence, the situation here is that how the problem is initially presented to you really does impact the kind of strategy that you use or the decision you make about, gee, I'm going to jump into it, I'm going to try that, or I'm not. Or given choices, which of the two you will tend to opt toward. So let's go back to the virus situation. Let's suppose specifically that we've got a deadly virus that is sweeping one of the Alaskan islands in the Aleutian chain. And the Center for Disease Control in Atlanta has actually developed 2 different possible solutions that may work, although, as you might guess, they've got some different odds of success. The island has 600 people on it in total. Okay, and all will die unless one of the programs is adopted. So with program G in this particular situation, what we've got is the likelihood that we can save 200 people on each of 3 attempts to do so, or on each of the islands that are infected across which we try this. The program G offers us the likelihood that every time we do it, all 3 times on all 3 islands, we could save 200 people each time with complete certainty. On the other hand, the other drug offered as drug H has a different set of odds with it, and that is that a third of the time you can actually save all the people on the island. But 2/3 of the time, the net result is going to be that you lose everyone. Okay, in other words, none of them are saved. 2/3 die. And in fact, what you're seeing there is a framing effect, because the net savings across 3 islands 3 times, depending on which of the 2 you choose, is exactly identical. In the one case, you're saving 1/3 of the people each time, so across 3 islands, you're going to figure to save all of the citizens in one island. And in the other situation, you're going to lose all of the people 1/3 of the time, but 2/3, sorry, it's the other way around. You're going to save all of the people 1/3 of the time, and you're going to lose all of them 2/3 of the time. But the net effect across 3 islands, when the statistics are all averaged out across many runs, is exactly the same in both situations. And so what happens is that which of these you tend to choose is exactly identical. And then let me put it to you in a slightly different perspective. And that is if I've already explained 200 are saved each time if you do G, 600 are lost 1/3 of the time if you go with drug program H. But let's set it up in a slightly different way. We've developed another drug, program I, which in fact costs us 400 people with a certainty of 1. That is, we are going to lose 400 people in each island where we apply this. But on the other hand, drug J, another drug program, CDC tends to be overly busy, I think. We can save 1/3 of the people 100% of the time. I'm misspeaking that. The odds of losing none are 1/3, 1 in 3. The odds of losing all 600 are 2/3, 2 in 3. And it turns out that if you do the math on all 4 of those, the net savings is exactly the same. The difference is that the choices I and J are actually presented in terms of the losses. G and H are presented in terms of the gains. But if you work out the math, it's identical. You're going to lose 200 people an island on average across the 3 attempts to do that. And here is yet another place where our decision-making tends to kind of mess us up. And one of the reasons that psychologists remain so interested in the work that Kahneman and Tversky started so many years ago. If we've given, as I've demonstrated, the fact that G equals I and H equals J in those 2 different scenarios, whether we go with GH or IJ as the choices that we make, what happens is that if G is greater than H, that is, if you choose option G more often than option H, the expectation would be that you should, faced with the death presentation, you should choose option I more often than option J. Okay? So that given the fact that all 4, G, H, I, and J, all lead to the same number of savings and the same number of deaths, if you prefer G over H, then logically you should prefer I over J. The math being equal in both cases, if your bias is toward G, it should be toward J. That's not what we find. What we find is that when presenting this to people, and the logic as I've described it to you, what they will opt for is they will take option G over H. But the same person, when faced with the problem described in terms of I versus J, will opt for option J. In other words, they will switch allegiance in terms of the decision-making that they offer here. And it comes back to the overall thing we're talking about here, and that is essentially framing effects. That is that the emphasis is different in the 2 cases. Logically and consistent with expected utility theory, if you prefer one, you should prefer the parallel in the other choice. And that's not what tends to happen. We tend to switch in that situation. So psychologically, the question then is, why on earth are we so inconsistent? And the explanation for that lies in the fact that if you look at option I versus J, the deaths are more prominent in I. That is, you're simply told point blank, you're going to lose 400 people with a certainty with 100% of the time. Whereas in J, there is ever that option that maybe some number of people can be saved. Okay. And so basically how the problem is represented carries a lot greater impact than the underlying probabilities in this case. And that in turn leads to another example. I'm still looking for that really nice itchy example that I had, and I hope we'll get to it later. Well, if not, you'll just have to wonder what it was. I'll try to remember it. So in any case, related to all this, there is another issue, and it doesn't look like the same, but it essentially is. Explanatory theories as to how we go about talking about or explaining why we do these kind of goofy decision-making options in various ways include things like what we would call sunk costs. Put this earlier. I jumped past it and I didn't realize I'd done so. But one other example of what I was talking about in framing effects is, look at another problem that I'm sure you've faced at some time or another. Consider the fact that a comedy team is coming into the university here. But unlike most university events, it's not going to be sponsored by your student fees. You're going to have to pay money to get tickets to get to see the world's most famous 21-year-old comedian. Okay? Widely ballyhooed. The show is going to be here at the UC. And you've got the opportunity either to buy tickets for $15 or $90. And let's do those as the two choices. Let's suppose that the comedian himself and the show, once it gets going, is absolutely atrocious. His reputation has way exceeded what is actually involved in what he presents. It's a lousy show. So you're sitting there in the show a third of the way through, having not laughed once, not being entertained, and you're thinking to yourself, I've spent $15 to sit here tonight. And you're having a lousy time. So ultimately you've invested $15 in having a lousy time. Those $15 are what are called sunk costs. Okay? That's basically what you invest anytime you buy entertainment tickets ahead of the event itself. Are you more likely or less likely to walk out of that comedian who is boring you, who's offending you, who is simply not funny, when you spent $15 for the ticket or when you've spent $90 for the ticket? Which would you be more likely to do? And by show of hands, I'll give you 10 seconds to make a decision, then we're going to have a vote here. Where would you be more likely to walk out, 15 or 90? And don't vote at all if the answer is, I'd stay either way. Okay? So where would you be more likely to walk out at $15 invested or 90? How many would say $15 and you'd walk out? How many would say $90 and you'd be more likely to walk out? Well, interestingly enough, the sunk costs in that situation, thinking logically, should not influence your decision either way. Because the ticket is already spent. The money is gone. Okay? And so really, the only thing that ought to drive you is whether you've got something better you should be doing or not. But that's unimpacted by the cost of the tickets. And I was with you, boy, if I spent $90, I'm going to stay here and suffer through this whole thing. But logically, that does not make sense. Because in fact, the money's gone either way. That is what's meant by a sunk cost. It's already been expended. Okay? I have that problem right now at home. I've got a lawnmower, a riding mower that's worth new about $1,000, and I've spent over $500 in the last year repairing it, kind of $20, $30, $100 at a time. And I'm like to here with the whole mower, but it's sunk costs, and I'm one of those, we're going to fix this thing. But I'll probably end up spending more than I would have if I just bought a new mower a year ago. So in any case, the underlying logic of that is counterintuitive, but the fact is the money's already gone. And if you enjoy being miserable, you might as well stay there regardless of how much you've spent. But how much you've spent shouldn't impact whether you decide to leave or not. Either way, the money's gone. Whether you stay or not, the money's gone. And so ultimately, you should make simply a rational decision. I have time I can spend better, or I can spend the next hour and a half more profitably this, that, or the other way, so I'm leaving, or not. Called sunk costs. So then we look at trying to explain all this, and that puts us into a variety of other kinds of theories, one of which is what is referred to sometimes as prospect theory. Okay? It's kind of a modification of expected utility theory, and it operates essentially on the basis of two underlying assumptions that dictate what this particular prospect theory will predict you're going to do in a particular situation. Utilities in general, the assumption is, are simply not evaluated absolutely. They're evaluated with regard to a reference point which you and I establish in the course of going through the various decisions that we want to make. Framing, for instance, as we were talking about, is but one among many factors that actually can influence where we set that reference point. But specifically, if we look at the problem that we were talking about earlier with the G versus H, if you think about what's being stressed here and the reference point, what most people tend to base their judgment on in the G versus H controversy, or decision, if we want to talk about it that way, is the absolute loss of 600 people, which really is the most prominent figure in the way this problem is presented. Okay, so in this particular instance, the stress on that is, gosh, we lose 600. And it becomes the reference point, and that puts us in the mode of thinking, well, we can at least guarantee to save 200. And so kind of the absolute size of the total loss that is potentially involved over here, what we tend to emphasize instead, given the magnitude of the loss that's being described, is the magnitude of those that can be saved in that situation. And the other factor that also impacts us in this situation is the idea that utilities are not multiplied by their objective probability of occurrence. They're multiplied by a very complex psychological probability. And we illustrate that over here. And that is that essentially on the I versus J combination, it's the reverse. That is, 400 lost is quite similar to the 600 lost in the different odds-based situations there. And so we're likely to be more likely in that situation to gamble to be able to save the 600. Because by presenting or emphasizing only the difference of the number saved in the context of a huge number that may not be saved in this situation, that order of presentation tends to lead us to go for the certainty that we can, well, gee, we're going to lose 600, but we can save 200 for sure here, cutting our loss to only 400. Over here, that's laid out specifically. But in that case, the difference between the various odds of losses makes us more likely to go with the odds, because then we're thinking in terms of, gee, there's a 1/3 likelihood we can save all 600. And we tend to get befuddled by the fact that, of course, the cold odds are that, as we pointed out earlier, both of these choices, G versus H, are identical to I versus J. It's simply that the framing effect puts more emphasis on the loss in the first situation and on the savings in the potential savings in the second situation, and that in fact impacts what we do. So the other part then that I was going to say is that utilities are not multiplied by objective reality. That is, we can go into Louisiana and we can work out using a calculator. In fact, they don't like us to do that. But in fact, you can work out the actual odds of winning in any given situation. And that's one of the reasons that card counters then operate. They have, a limited number of mathematical genius. In fact, there was a movie here just in the last couple of years about a group from, do I remember, it was MIT, that went into Las Vegas and were really quite skilled at what they were doing. They had to spend a lot of effort at disguising themselves so that it wasn't obvious what they were doing. But it was clear that that was an effective strategy, because that game of chance is operating on the idea that chance is the only thing that's operating. And if you have the mind to keep track of the fact of the number of aces, kings, queens, jacks, and tens that have been dealt, and you can keep that in your head, it makes it much easier to predict the odds that you should bet at any situation on a particular hand, because then you can assume that they're drawing jacks or the color cards, the face cards, or the aces. The odds of drawing that go way up if very few of those have been used in the first half of any deck that's being used. And so in that case, the reason for the casino taking very legitimate objection to that strategy is that it's biasing, it's altering the bias, and ultimately they're only running potentially on a 1 or 2% margin on some of those games, at least the ones they advertise. And so that's the reason they don't like it, because something like card counting biases the odds on which the thing is fairly supposed to be operating. There's another way to diagram this, which may lose you, and it may in fact aid what's going on. I found it to be a little bit helpful. But in essence, I've already said this, but I'll spell it out for you graphically. It's the creation of that psychological probability that makes the problem solving so interesting as a psychological concept, and it's the reason that Kahneman and Tversky really put their fingers on something that has fascinated psychologists now for 4 decades, essentially from the time it was originally published. And so in essence, this kind of a model is actually related to prospect theory, and go with me here for a minute while I show you the following. Okay, if the probability of an event is actually going to happen is this, the objective probability, those are the odds that we were talking about, and whether we're talking about how do we treat a particular illness, or how are we going to bet on this kind of odd situation. Those are the actual probabilities, the objective, this is what will happen if there's no bias. But let's put that up against what we're going to call pi here, and that is the specific probability that we assign to it. Okay? And so pi is associated with a probability. A different pi is developed for each given situation in our head. That is, this is the decision making that we actually use in a given situation. And that's what is impacted by how the problem is actually presented. But in essence, what happens here is that in this particular situation, this is what theoretically ought to happen. That is, if you're following the odds precisely, independent of how the problem is presented to you, once you know what the odds are, the dotted line would represent a precise correlation between this is what the odds say will happen, this is what experience over time says will happen, and this is what you assign to it. Okay, this is your subjective probability in this situation. So if you're being absolutely coldly rational, given what the numbers are telling you, this is the kind of curve we would get in this situation. In essence, what tends to happen in most situations is that the pi factor has this kind of an effect. That is, relative to optimal decision making, we tend to pull off in the direction of our perception of these actual odds rather than the actuality in that case. And it's those specifics that we're trying to pair up or trying to identify that really become the basis for all the studying that we do. Another way to look at this is to think in terms of what is called regret theory, as a kind of emphasizing the losses in a given situation. And I guess there are some gamblers coming out of Louisiana that probably do have regrets. But in any case, we'll pose a couple of more problems to you and illustrate what's happening. Let's go back and look at, the specific one that we had earlier here. In the first pair of options for the Elias paradox, pay attention to the 1% likelihood of gaining in choice B. There's a very small likelihood that this is going to happen. But what happens is that this theory assumes, that is, the regret theory assumes that we overweight that. Okay? What happens is that 1% tends to get magnified in our head in the following way. Okay? It grows bigger and bigger. And I've never figured out why this thing times. It was supposed to lay out perfectly evenly. And of course, what happens is it takes a long while to get to the big fat zero that you carry with you as you think about that. There's a very small odd it's going to happen, but that ends up taking up a big component of our decision making. We way overweight the loss, or the how bad we'd feel if the particular zero loss happens. So both of the prospect and the regret theories attempt to increase the predictability of our irrationality in decision making. The latter, the regret theory, really emphasizes the importance of factoring in feelings of regret anytime we evaluate a problem situation. Excuse me. That is, to what extent are we not going to feel good if the worst tends to happen in a given situation? But really, more importantly in this, what is important to realize is that both theories really recognize that we have limited resources available to us in calculating the odds, in really estimating what the net effect is of this, that, or the other kind of decision across anybody else who's impacted and so forth. And to figure that out, we have to process huge amounts of information that may or may not actually be available to us in a given situation. And that's what makes it so problematic and why it comes back to the fundamental, the feelings that we walk in with, essentially a little bit of what we were talking about in the interview last time. And that is that in essence, it's the feelings that do also impact the rationality, theoretically, that we use in a given situation. So an obvious question then is you can see we're still worried about that $0. It hangs with us. We do not like to lose money. So in any case, how do we handle complexity? Think about that for a minute, because you face it in your career. You're now in a junior, senior level course, and therefore you're arguably within some degree of eyesight, perhaps, of graduation. It's going to happen at some point. This doesn't necessarily, in some years, it's not the best of all possible times to come out. And so when you finish up your bachelor's degree, you've got to make some decisions. Are you going to take a job? Are you going to hold back and go into graduate school? Are you just going to get married and let your wife work while you do the housework? Evaluating all of those choices could become mind-boggling in terms of the rationale that you have to reach in a given situation. And that's one of the more complex problems that you face here shortly. Let me step out of the context of cognitive psychology for a minute and offer you some particular information, and that is that one of the strategies that people tend to say and offer is essentially, I'm going to take a year off. I'm going to finish in December, or finish in June, graduate in May, whatever. And I'm going to take a year off. I'm going to kind of organize myself, get myself grounded, and then I'm going to apply to graduate school. I would strongly urge you as an academic advisor, as a faculty member, against that strategy. And I'll give you a very specific reason why, and it's probably one that you haven't thought about unless you've listened to me before. And that is that if you think about your career, let's just arbitrarily say you're going to educate yourself until you're 25, excuse me, and graduate at 65. So we're going to say you're going to have a 40-year work career. Well, let's be honest. Let's say 67, since they're now. And in fact, they'll probably have Social Security up to 70 by the time you do graduate. So let's say you're going to do a 50-year career from 20 to 70. One of the factors related to your career is the fact that your pay in general goes up steadily, partly because of inflation, partly because of the fact that industries that want to keep you will promote you. So built into the way our American industry and careers work, you can count on the fact that once you start working, assuming you're doing a reasonable job, a commendable job, you get raises. And the net effect is that your average salary goes up. If you put that onto a lifetime earnings graph, 20 to 70, and plot that out, the curve is going up. As you're looking at it, the curve goes up. 20 to 70, the earning curve goes up. The effect, if you take a year off, is that you take that curve and move it 1 year over. Okay? The point being that when you enter any career, you're going to have to start at the ground level, at ground level salary. And then as you move beyond that, you get raises and you move up the hierarchy. But in fact, for most people, their highest earning year is among the last years of their life. Work life, I mean, not that you're going to die as soon as you quit working. But the situation is simply that people don't tend to keep in mind that, well, I'm going to take a year off. Well, what you're doing by taking that year off is costing yourself your top year of earnings in terms of lifetime money on which to retire. Don't lose track of that when you're thinking about stepping out. I'll get back in position so I'm not threatening you so much here. Let's talk about that issue of complexity, basically, and how do we do it? Well, there are a couple of different strategies that we tend to follow, rather interestingly. One of them is to do what is called satisficing. Okay? In this situation, we don't seek the optimal answer. What we seek is a satisfying answer. Yeah, given the logic of what I ought to do, there may be a criterion that we can rank order of what you really ought to do. But ultimately, there can be a lot of different reasons why we may not be able to. Give you an example. Suppose you're trying to you're going to take a vacation and you want somebody to babysit your house or your apartment. You want a house sitter or an apartment sitter of some sort. There may be thousands of such people available among fellow students here at the University of Houston who'd be willing to do that for you. That's one obvious place to look. You don't have either the time or the interest in actually interviewing many students to find who would be best. You just want a satisfying one. Okay, one that will kind of meet your goals in that situation. And so what you probably will do in that situation, if you're engaged in satisficing, is to sample among the alternatives that are available, the students who would be willing to help you with watching the house. And then in that sample, you'll simply draw an appropriate representative among the ones that you look at. So you kind of, you've got thousands you could interview. You interview 10 friends or 15 or whatever and randomly select among those. You don't have time to sit down and ask each person how they're going to deal with the cat, the dog, and everything else. Another possibility, other than satisfying, is elimination by aspects. That is one of the ways you could look at making a decision as to who ultimately to hire to protect your property, is to simply rank order for yourself what is the most important thing you're looking for, what is the second most important, and so forth, and just have a rank order list of what is most important to you. In that case, in all likelihood, given that you're going to give them a chunk of change, probably some at the beginning and some at the end, for almost all of us, reliability would be number one. That is, having paid them cold hard cash, we want them to do what they've committed to do. So reliability becomes one of the things that we look at. But suppose you've got a cat. Sensitivity to animals suddenly jumps very high on the hierarchy. Okay? The ability to recognize problems, to walk in and realize, wait a minute, the lights in the bedroom aren't working. Why is that? Should be a question that should occur to a housekeeper, or if the lights are entirely off, or the air conditioning is, I mean, you can name all the different problems that happen. But that person you hire has also got to be able to recognize problems as problems and then be smart enough to figure out where to go to fix it. I mean, you'll pay for it, it's your house, but somebody's got to be there to identify, gee, the air conditioning isn't working. The fish are kind of hanging off the bowl, and that's a bit of a problem. So you got to be able to recognize that as a problem. So those are the kind of things that you and I put in a rank ordered list of what we're really looking for. And if you followed it to its logical conclusion, it's kind of like the cold hard problem solving strategies. You would come to a decision across the many that might be interviewed and find the actual correct answer, the correct person to choose. But what may happen is that what you've got to do in that particular situation is simply interview the number that you have time to interview, and then relative to your priorities, you kind of create a grid. Person A, here's how he or she ranks against reliability, sensitivity to my cats, identifying problems, and so forth. You've got to rank order them. And among the ones that you do have time to interview, you then look at, okay, this is number one priority, so I'm going to eliminate anybody where reliability is not number one. And then you collapse a little bit. You look only at those where reliability is available or is obvious in them. Then you look at the number two category, and across all the people that are sensitive to cats, you pick only that are not sensitive. Across all, let me start again. Across all the people relative to cats, you keep only those that are sensitive to cats. This is not as hard as I'm trying to make it. And so forth. And depending on how many hierarchies you have, you may be able to elegantly work yourself right down to point number one, where you've got one person who's reliable, sensitive to cats, sensitive to problems, and so forth. But on the other hand, time, again, may pressure you so that you simply select the best among the people that you've interviewed. And it's based essentially on the aspects that you've rank ordered from most to least important. A third possibility is in many ways similar to the last one, and given my over-detailed description, I may have covered most of this, but essentially similar to the last one, but essentially candidates may be selected based on the adequacy across various strengths on a variety of different criteria, which is essentially what I was describing in the elimination by aspects. The difference, I think, between elimination by aspects and clustering is the fact that what you've really done is to prioritize the rank orderings in the clustering situation. That is, you've really put the things that are most important to you at the top. And in the elimination by aspects, you've just kind of listed them all and simply kind of maximized the number that you can touch in a given situation. And another possibility is another factor that really governs this, and I've essentially implied it in what I've been describing here so far, is the fact that in making this kind of relatively complex decision, we have to essentially adapt to circumstances. That is, at some point, if the plane is leaving for Europe on a Sunday and you don't start the selection process until Saturday, you've got only a certain amount of time to eliminate the aspects, but you run out of time. Okay, you eliminate by aspects, but you run out of time, and therefore what you do is simply select randomly among those that are still left. So in some ways, adapting to circumstances kind of compromises everything you've tried to achieve by the others. But if there's any ability to rank order those priorities, it's going to lead to a better decision. Let me go back and review here, because it will probably now make a lot more sense, the heuristics that Kahneman and Tversky were talking about. And that is the various strategies for dealing with the complexities that we've just been talking about. You will remember that we talked about the fact that they're used by both novices and experts alike. We all use them in trying to get control over the complexities of decision making. Essentially, they are very hard to overcome. That is, when you and I have experience in a particular area, it's very hard to step beyond that and try to make the decision on another basis. And anybody suggests that, oh, you just do, you're very likely to kind of rear up and argue, no. These are what are important to me, and that's really, we're just anchored in our own heuristics, because they're developed, as you know from the fundamental definition, out of experience, out of our own experience, and that's a very hard thing to move up beyond in many ways. The various heuristics that have been developed by Kahneman and Tversky actually fall into a cluster of fairly obvious kinds of different approaches, and what's really involved here is kind of identifying wherein the vagueness lies. That is, to what extent things do or don't work well in the strategies that we base simply on common sense and experience. The experience is not always applicable. The common sense may not, in fact, govern or control all the things that it should. And that leads to the kind of vagueness that's built into heuristics. But by their very definition, something like an availability heuristic is simply, as you remember, defined as the tendency to make a decision based on what exemplars come to mind. That is, when you look back across your experience base, what have you seen that bears on the nature of the problem that you have right now? And these lead into just a marvelous array of samples that I've already told you or shared with you a couple of times before. These are different ones, so I can tease you in different ways here. But how many words do you think are in English are constituted of words where N is the next to last letter? The only one I could think of immediately was onions, as I was thinking of in writing the material here earlier. But if you think about it, there is a much broader group of words that don't involve necessarily N in the next to last position, but every word that ends in ing fits. And when you capture it in that direction, if the example that pops to mind is not next to last letter is an N, but rather how many words end in N, That's a much easier problem to solve. And in fact, the data that's been done by several people across the years argues that you'll get 5 or 6 times, literally 5 or 6 times as many examples when you put it in the more mindful or more reminding element in this kind of a situation. Being reminded, hey, stupid, ing words always have M as the next to last letter. That really increases the likelihood that you'll get correct responses, or a number of correct responses. Medden and Ross did a very good study on that back in 1992, for instance. Solo exemplars are also important in the availability heuristic, and we didn't really talk about it in that situation. But consider the following: it's very tempting to anchor this in racial terms, as some of the initial work was done. But what's really being suggested here is not so much race as isolatableness, if you want to think about that. So I decided to do it in terms of purple and blue rather than black and white, or any other minority operating in a group. It turns out that the effect that you can have as an isolatable person in a group goes up as your uniqueness increases. That's kind of the underlying premise of what that work based on race was really talking about, is that if you're if you think about it for a second, and do it in terms of race if you want, if you have 3 blacks and 3 whites in a group discussing this, that, or the other aspect of whatever decision needs to be made, it's much less likely to break down as the blacks think or the whites think when you've got 3 of each representatives. But if you have a single representative of either race, that issue of race is more likely to crop up. And really, as I was thinking about that as an example, because I don't like it as an example, it really comes back not to race, but to identifiability. The extent to which you can be isolated as a unique person making a particular combination, or a contribution, I should say, really increases the likelihood that those odds will stand out, or that your beliefs will dominate in a given situation. Couple of different bases for explanation of that, but if you think about it, people who speak a lot in a meeting tend to have their way more often in what the group ultimately decides. And it's at least partly because they're priming the availability thing. They're giving you so many different reasons for whatever they're arguing in favor of that they tend to dominate the discussion. But it comes back to impact. That's what you tend to think of when it comes time to vote at the end of the meeting. That particular view has stood out in that case because of frequency, or the fact they're using an Irish brogue, or any of a number of different things. But if you're an isolated person in a larger group of people who are otherwise similar, it really increases your power to influence that group in really demonstrable and significant ways. And that goes back to the availability hypothesis. You're the one they tend to think of when they're coming back to kind of summarize what happened in this particular situation. Your familiarity, your isolatability increases the power of the argument that you raise. Let's review briefly another one that we looked at, and that was essentially representativeness. And that, of course, is simply the tendency to, we'll eventually get it here, back up. I hit too many buttons. Why is this thing fighting me here? There we go. That the representativeness heuristic is simply the tendency to judge the probability of occurrence of any event by its similarity to the typical features of the particular event that's involved. There are 2 factors psychologically that contribute here. And that is, let me give you a specific example, then we'll talk about why we tend to vote as we do in this kind of a situation. Think about the effect of contributing factors in the representativeness heuristic. And that leads to, particularly, one of the driving factors in you and I is the fact that we fundamentally do not understand what is implied by conjunction. Okay? Give you a specific example. Let's suppose we're talking about teenage deaths, and the way this is expressed, it's like I'm expecting every teenager to die. I'm not talking about that. I'm talking about the subset of those teens who do, unfortunately, die for whatever reason. Okay, and that's the core of the issue that I'm raising here. But if you look at these different choices, will a teenager be most likely to drink too much and die? Could we say simply a teenager will most likely kill himself? Could we say that a teenager will most likely drive, I'll get it right eventually, drive too fast and die? Or that they will become depressed and die? I won't ask for a show of hands, But did you pick one of those as the answer that you would ultimately defend? There is data, of course, to look at. One of the things that I always use when I'm discussing this in the introductory course is simply the idea that given the fact that you're inherently healthy by the time you get to the teenage years, the odds are very low that you're going to die there. But all of the major killers of teenage adolescents, if you think about it these days, are not biological, they're psychological. Every single one of them has a psychological basis, fundamentally, not a biological basis. And of course, we've always built I say I'm campaigning to other faculty here, but in essence, when you look at the requirements in the university right now, they're very enamored of the idea that we need to do physical sciences. Well, that was true 50 years ago when the major problems we faced were diseases. That's not true now. It's things like suicide, drug problems, alcohol problems, and so forth and so on. The basic problems that we face as a species, certainly in the teens and 20s, are psychological, not biological. So in any case, which one did you go with? I'm not asking for an answer, but think as to which one you went with. And I'm going to pick out what logically would be defined as the only one you really ought to be checking, and that is this one. Okay? And it's actually implied by the conjunction in the probability, the fact that each of the others has an "and" clause in it. And so if we look at number one, teenagers may be likely, in the instance where death is going to result, to drink too much and die. But in fact, all three of those other causes involve "and die." And so the idea is that the more generic statement, the one that really fundamentally reflects what's going on across all of those other explanations, is the fact that they die. They kill themselves, whether through drinking or driving or depression of one sort or another. And that is the fundamental reason that I cite, that psychologists cite, the idea that when we screw up in the availability heuristic and the various heuristics that we're talking about here, one of the bases for that screw up is simply the fact that we fundamentally do not understand what is implied by a conjunction. When you do A and B, C and B, D and B, the common element across all of them is B. That's the conclusion that is most generally justified in that situation. And the other one that is also a misunderstanding has to do with the relative misunderstanding or misconceptions of the roles of chance, the impact that chance has on the various kinds of decisions that we may make in any particular situation. A classic example of this you're already familiar with, and that is if I flip a coin this many times and the result is a head, what am I going to get next time? What do you bet I'm going to get next time? It is so tempting to jump in there and say, well, look, all those heads, it's got to be a tail. It's got to be. Because we just don't get it. I mean, you never see 6 heads in a row. Well, you never see 8 heads in a row. You never see 3. There are a lot of ways to rationalize it. But in fact, the odds that next coin will be a head or a tail is 50-50. And if it happens to be on the next toss that it's a head again, yeah, it's an extended string. But in fact, that string doesn't impact what happens to the coin on the last time. It does impact how we analyze it. Okay? And in essence, what we're misunderstanding there is the law of chance. If the coin is unbiased, the history of its operation doesn't impact how it operates now, if it's unbiased. Okay? And people tend to lose track of that. The fact that you've got 5 in a row of a given thing doesn't necessarily guarantee that the last thing is going to be yet another of that event, or that it's going to arbitrarily change it in any specific way. And then I have another example that in some ways, as I think about it, really doesn't fit, but it does, and you'll see what I'm talking about here in a minute. Professional basketball and baseball teams face a problem, but let's set up the following kind of a scenario. Let us suppose that it's alleged in basketball and in baseball particularly that players have streaks. Okay, that a given player has a streak one night. He's really hot and hits whatever number of points. Really, that is directly analogous to flipping the coin. Okay, he's shot, he's hit. He's shot, he's hit. He's shot, he's hit, and so forth. Or in other cases, they have strings that are negative. Hit, clunk, hit, miss, hit, bounce off the backboard, the chorus, the crowd is harassing him, and so forth. The question is, when that game comes to the end, who do you give the ball to? If it's right down to your team or theirs in a tie game, who do you give the ball to make the last shot? And the answer, logically, and it has been demonstrated by actually studying the Philadelphia 76ers, one of the better-known basketball teams. Somebody actually went back over a 5-year period and looked when that situation had occurred, and the answer is really quite straightforward. And that is, what you do in that situation is to give it to the person whose shooting average is highest. It does not matter whether they've had a rung of clunkers. You still give it to the person who has the highest overall shooting average, because in the long run, that average reflects an extended experience. And that is the person who should have the ball at the end of the game. That is the reason that the defense always clusters around whoever is the team's star in any given situation, when it's the end of game situation. But it comes back just to fundamental appreciation of statistics, and that you need to play the odds in that particular situation. I'm going to cut off the lecture here just slightly early because I'm about to jump into two other illustrations of heuristics that we'll be talking about. So we'll pick it up and wrap up decision making in the early part of the next lecture.